Okay, just I am going to discuss some general aspects, then we will go to the real topic, okay? Actually, from this time ahead, we will be discussing our numerical method systematically, starting from the root finding technique to differential equations, okay? In this way, we will move. Lots of methods are there, but at this stage, because of your time constraint and the level of your understanding, we will be introducing the thing consistently. We will not be going to some higher order, something that is not actually achievable at this level. So in order to proceed with, we have to understand first that in which areas of our learning, okay, we will need our numerical technique and how they will be coming to us and how to handle them. Actually, if we we are discussing chapter 5 ahead of your book that deals with the finding the roots of some algebraic and transcendental equations. Actually, in your earlier level of learning, did you find any instances in your electrical engineering courses where you found the root of equations? I hope you can hear me.
Yes, sir. We can hear you, sir.
Hey, can you hear me? Because I am disconnected.
Sir, we can hear you, sir.
Yes, sir.
Then why don't you respond? Because I have not found, for example, anything there in your understanding of your earlier 4 or 5 semesters where you found the root of some equations that is applied to your electrical engineering.
Yes,
In,
sir.
in which course? Actually, the thing is that my way of teaching, I would not say teaching actually, my way of learning is something like that, interactive type, okay? It cannot be one directional, okay? Whatever your teacher is saying, you are believing everything. This is not the way of understanding. You have to participate in your learning and you have to relate something that you are learning with your previous understanding. Otherwise, you will never feel the importance of learning a particular course. We are not dealing with something that is very discrete one. We are dealing with something that has some relationship from your from the earlier level. For example, say I am asking you one fundamental question because you have learned electronics in your earlier level. For example, say we have a diode circuit, something like this, okay? Your current is flowing in this direction, I, and your voltage is there at VD diode voltage. Can you find I? I equal to what? Hey, when you have been introduced with electronics, probably this is what the first type of electrical electronic network that you have been introduced with when a PN junction diode is introduced, isn't it? Didn't you find, for example, the current of this type of circuit in your electronic course? If you
yes, sir, we did. Yes, sir.
If you did, then I am asking you what will be the ID? What is your
Sir,
I?
I know e to the power minus a v n by vt, something like that.
So something like this, that your understanding from a student. You are talking to a teacher, okay, not to your friend. Be careful about that. Not something that you can utter.
Sorry, sir.
You got my point? If you
Yes,
cannot do that, your learning or your investment of time and money has no value. Be careful about that. Okay?
yes, sir. Sorry, sir.
to be very careful, it is not actually possible to solve this for this current if you know the exact diode current equation. If this is not available with us, what we usually do, we draw a curve something like this. This is your diode voltage and current. Okay, we have a curve something like this. This is your the VI characteristic of a diode, isn't it? Then
Yes, sir.
on top of it, you have to draw a load line. Have you drawn the load line in electronic course?
Yes, sir.
That it intersect at a particular point. That point is the value of your diode current, isn't it? At that particular bias voltage, okay?
Yes, sir.
So now the thing is that either you need to have this curve with you to find the solution, or you might have an approximate equation of this curve. That equation is usually say Is into e to the power say V divided by Vt minus 1, something like this, isn't it?
Yes, sir.
And your Vt is actually a constant depending on type of the material that is used there in your PN junction. It depends on the charge Q, and as well as it depends on a constant. It is called Boltzmann constant. So by using these things, that current voltage Vt can be calculated, and eventually you can plot this curve with respect to this is your diode voltage. So if this is the case, then you can easily use this equation there to find your current, and you can solve them for your diode voltage to achieve or a particular diode voltage, what will be the current, or you can easily find what is the point of intersection between the load line and the curve, then you can find the current. Okay, so in this way you can find, you need to find the root of this equation. Okay, similarly, if we have an impedance of an RLC network, say RZ, and magnitude of the impedance is equal to what? It is not equal to say R square plus omega L minus 1 divided by omega C square, is it?
Yes, sir.
So if I ask you, for example, say that a R value is given, say R equal to say 10 ohm, and say your L value is given, say L equal to say 1 Henry, for example, and say C equal to say 0.5 farad or something like this. And you have been asked to calculate the value of omega, the frequency at which your Z magnitude of Z will be a value equal to say 10 ohm. Can you find the value of omega?
Yes, sir.
Then how it will look like actually? Is it not something like that? It is equal to 10 minus square root of say R square plus omega L minus 1 divided by omega C square equal to 0. Is it not something like this?
Yes, sir.
Yes, sir.
Then if this is you can call this equation as a function of omega and set it equal to 0. Then
Yes,
you solve this equation to find the value of omega, isn't it?
Yes, sir.
In this way, so this is also a root finding technique. Okay, root means a position at which the value of your function is equal to 0 at the independent variable. So in this way, you can find the root. But sometimes you can use your analytical equations to find the root, or you may need, for example, some numerical technique to find the root. Your equation can be of this type, or equation may contain some logarithmic and trigonometric functions that we call sometimes transcendental equations. Okay, for example, say if I ask you to find the root of the equation, say cos x minus x equal to 0, can you find it by analytical technique?
Yes, sir.
Say cos x minus x equal to 0. Okay, this is your function. You have to find the value of x. Can you find it?
Uh,
Okay, let us consider that we are using some other technique, a simple heuristic type by which you can find the value of x iteratively. Okay, you can arrange this equation into two forms. Either you can write this equation equal to x equal to cos x, or you can write x is equal to cos inverse x. Can you write it?
yes, sir.
This is your one form, this is your other form. Now let us start from, okay, if we plot this curve, you can easily find that how your plot will look like. Graph plotting is one of the important issues of our understanding. Be careful about that, okay? So this is your cost curve, isn't it?
Yes, sir.
And your straight line is, for example, another is this, something like this, okay? So if we add these two curves together, you will get this thing, isn't it?
Yes, sir.
Then you will see that the value at x equal to, say, this is your x value, this is your fxa. Then at the point x equal to, say, 1, you will see that this is what the value, okay? Now you see that how many roots can be there. It is going down actually. And the maximum value of cos is equal to 1. So eventually, it will, how many roots it will have actually? Because in this region, your function value will be equal to positive or negative.
Negative.
Negative. If they are going all the way negative, is there any possibility to come to 0?
No, sir.
No, sir.
So then in which region there is the possibility to come to 0? Is it not within this region?
Yes, sir.
When, for example, these two values are equal, isn't it?
Yes, sir.
So that value, for example, will be lying between 0 to pi by 2 actually. So your x value will be between pi by 2 to 0, okay? Within this region, you will have a single root of this equation. That you can say estimate. Now, if you want to find it by using some iterative type technique, that means by some repeated calculation, okay, you have to start from an initial point. Say, let us consider that we are starting from x equal to 0. This is what our first guess. If our first guess is this, that we are using equation 1, then your next value of x1 would be equal to what? Cosine 0, isn't it?
Yes, sir.
Would be equal to 1.
1.
Then your next value would be equal to x2 would be equal to cosine 1, isn't it?
Yes, sir.
Would be equal to 0.5403 or something like this. Your x3 would be equal to cosine 0.5403, okay? You can have some value. Similarly, in this way, you can keep going. When you will see that x value of your previous iteration k and your x value of your next iteration k plus 1, this absolute value xk plus 1 minus xk is greater less than equal to some specific error criteria, you can stop this calculation. Can you do that?
Yes, sir.
So in this way, you can easily find what is the value of x very easily. Now, we have a second equation, okay, 2. That 2 is also the alternative form of the original equation. And our starting point is same, say x equal to 0, okay? Then your x is equal to cosine inverse 0, equal to what?
Uh,
Within the range 0 to pi by 2.
1.57.
Is it equal 1.5?
707.
Is it not equal to pi by 2?
yes, sir. Pi by 2.
Yes, sir. Perfect.
Okay, so this is your x1. Then your x2 equal to, then again cos pi by 2 equal to 0, isn't it?
Yes, sir.
Then your x3 equal to cos 0 equal to pi by 2. That means your solution is toggling. Your solution is toggling back and forth between this point to this point and that point to this point, isn't it?
Yes, sir.
Will you find any solution?
No, sir.
Impossible. In this way, it is, that initial value will not give you the solution. Can you change the initial values a bit? For example, say x is equal to x0 is equal to, now without considering 0, say equal to 0.2. Can you proceed with the calculation? Then your x1 would be equal to what? You see that your calculation should be made in what? It should be in the radian mode because x is your radian, isn't it?
Yes, sir.
So if your x, let us go there. Okay, if your x is equal to 0.2, then your x1 would be equal to cos inverse 0.2 would be equal to 1.369, for example. Then your x2 would be equal to cos 1.369 equal to what? Cos inverse. You can keep going repeating the calculation by using your calculator.
So error আসছে, sir, syntax error.
Why?
So cos inverse 1.369, sir.
Cos inverse function cannot be greater than
1.
1.
yeah, because it cannot be greater than 1. But this calculation is correct then? Cos inverse 0.2? Probably
Yes, sir.
not.
Cos
Cos inverse 0.2 equal to 1.36.
1.36.
But you see that because you see this value of cos cannot be, argument cannot be greater than 1.
Yes, sir. Sir, I think say x2 should be cos of 1.369.
But if it is not, then cos inverse 1.57. It cannot be greater than 1 actually, okay? Then what you need to do? You just proceed with another initial value, say x is equal to say 0.4. What will happen?
Sir, the value is still greater
1.15.
than 1.
Still greater than 1. So this equation will not work actually, isn't it? So in order to have the iterative solution, you have to pose your equation in such a way that it is converging to a solution. Okay, so this is another way of finding the root, but it may not be possible in many of our instances. Okay, so the technique is what? You can use some graphical technique, for example, to find the root. For example, say, if we have a function, that function, this is say x, this is your fx, okay? If a root is there somewhere, then what will happen? It will cross, for example, the axis, x-axis, and the value of your function, for example, just before the root or just after the root, you calculate, you will see that it will change the sign, isn't it? If it changes sign, then you can find see that it will have a root, something like that. But those techniques are actually generalized in a form that is described in your book. I am sharing the book with you so that it will be easier for you to look at where you are. All these techniques are described in chapter 5. Okay, there exist many algorithms for finding the root. We are discussing for the real root now, but some techniques are there to find also the all complex conjugate roots also. As you have known that if you have a quadratic equation, you can find the roots of the equation by using an equation that you have learned from a very earlier level. That if your equation is ax square plus bx plus c equal to 0, then your root will be minus b plus minus square root of b square minus 4ac divided by 2ic, isn't it?
Yes, sir.
We have another variant of this equation. Okay, try to, for example, learn about it. That this is one form, we have another form. And in many of the cases, this form that you have known will not work. The reason is that a subtractive factor is there, b square minus 4ac. That factor is very crucial in determining the roots of a quadratic equation. Many of the things are there. You have already known that how many types of roots can be there for a quadratic type equation. So we have a graphical technique that I discussed earlier, that if we can graph the function, then you will see that where the location of the root is and you can calculate the root. But if we, but still by using it with the help of graph, we can have some bracketing technique to find the root. That if we have the graph already, I have talked about, This example is taken from chapter 1 of your book, but this example is very similar to the example that very similar to a problem that we have in our electrical engineering. Like if we have an RL circuit, then current through the RL circuit equal to what? E divided by R into 1 minus e to the power minus R divided by LT for time t is greater than equal to 0 if the inductor is carrying no current. If you say E value is given, say E equal to 10 volt and say L equal to say 1 Henry, and you t equal, at t equal to 1 second, if your current, for example, I equal to 5 ampere, then in order to have the current I equal to 5 ampere at t equal to 1 second, what will be the value of R? Can you find it? That your equation will be equal to 5 is equal to 10 divided by R into 1 minus e to the power minus R, isn't it?
Yes, sir.
Can you solve it for R?
Yes, sir.
Then if you want to solve it, you can find a function fr. That fr equal to would be equal to 5 minus 10 divided by R into 1 minus e to the power minus R. This equation is not that simple to be solved by using analytical method. So what you need to do, you can plot this function. If you plot it, your plot will be looking like this. Okay, it will cross axis. For example, if you plot, this is your R, this is your FR. Then say it will be taking the shape. At this value of R equal to R0, you will have 5 ampere of current I equal. The solution is done. Or you can use the bracketing technique, for example, to find the solution. In this case, what you need to do, if we know that with this vicinity, say this value is equal to say RL, lower limit, this value is equal to RE with the upper limit. Within this lower and upper limit, you will have the root. Then we can gradually shrink, for example, this bracket gradually towards the root, and eventually they will coincide with the root. Okay. Now the question is how to shrink this. There exists some technique. One is called incremental search type, where we can incrementally proceed between the limit to find the value of the function and examine at each stage that whether the value is changing sign, function value is changing sign or not. If the changes sign, then we can assume that your root is, we can say that your root is there at this vicinity. Or we can gradually half the limit x RU and RL, then we can repeat the process to find the solution. Okay, this technique is called bisection. From now on, we will be discussing the thing. Okay, now the thing is that if your function is continuous, you look at the figure in the left side, you will see that you have 4 figures there. Okay, if you have a function fx, then that function is continuous, say between 2 intervals, xl and xu. Then what will happen if we can evaluate the function values at xl and xu, then examine their sign. That means if we multiply the value of xl and xu, and if that multiplication will be less than 0, that means one of the function values, either xl or xu, has opposite negative sign and another is positive, or vice versa. Then we can say that your function is crossing the x-axis between these 2 limits, and that crossing can be something like this. It can have a single root, a single root can be there, or some odd numbers of root can be there. Is it okay?
Yes, sir.
But your function value may not change, for example, the sign. In this case, what is the conclusion? Your conclusion can be no change of sign is there because both function values are positive. So no root. Or it can have even numbers of root. Okay. The condition, this proposition is valid, or this thing, if your function is continuous between them, and your function has crossing your axis, for example, very axis clearly. But if we have our function that might have something like this in the right figure in the right, okay, figure 5.3. These are the exceptional cases where this algorithm may not work. In this case, you see that if your function is discontinuous, figure 5b, 5.3b, although the changing of signs are there, but between these two time interval or bracket, no root is there. And you figure a root is there distinct, but another root is there. That root is located, for example, tangent to the x-axis. Okay, that means a multiple root can be there at this location. But we will be discussing, for instance, very simple cases first. Then your bisection algorithm is actually there. Okay, you try to go through it. These are simple things. Your bisection algorithm is this. We'll when we will be talking about a particular problem, then it will be more visible to you. Let us proceed with theoretical aspect first. Then I will show you a solution of a problem from your book that shows the application of this technique. You see, equation 5.1 is the test equation. Okay. If you have your upper limit and lower limit known to you, and you are selecting these two limit, then you evaluate the function at XL and XU, multiply them. If they are less, this multiplication is less than 0, that means you have a root between them. Now the thing is that next step is what? You have to shrink this bracket in a way so that they will be coinciding together at the location of the root. So that one technique is incremental search technique, another technique bisection. So will be bisection technique will be used there. In this case, once this is satisfied, equation 5.1, then in the next iteration we will have the bracket. That means the next thing is that the location of the root in the first iteration would be equal to XL plus XU divided by 2. Then at this new location, we evaluate the function. Okay, let me show it graphically, then it will be more easily understandable, I think. Okay, let me erase first. For example, say this is your function, okay? This is x, this is fx. This position is your XL, this is your XU. Now you see that at the first, this is your initial position, okay? You are calculating the value of the function and finding this condition satisfied. So your root is there between XL and XU. The next thing is that you find a position, say C, that C equal to, say, XL plus XU divided by 2. You are just having that section. Then consider that this is your C. That at this stage, what you need to do, you have to calculate your XL value is calculated, then you calculate FC. This is 1. Now you check whether this condition is 0 or not. For example, in this fictitious type of problem, is this condition will be satisfied? Hello.
No, sir.
No, sir.
Why?
Sir,
Because
FC is a negative value.
FC is negative, then FC and FL both are
Oh,
negative.
negative.
Okay. So this condition is not satisfied. If this condition is not satisfied, then your root is okay. Now, will there be any root between XL to C?
No.
No. Then your root is lying on the other half, okay, from C to XU. That in this case, you can replace your XL by C. That means your bracket is shrinking in this direction, isn't it?
Yes, sir.
Now again, you, for example, half it, okay? In the next iteration, your half will be equal to C, say C plus XU divided by 2. Say this is your C1. Consider that this is your C1. Now, you evaluate the function at C1, FC1, and multiply with XLAU that you calculated earlier. In this particular fictitious example, is this condition is satisfied?
No, sir.
No. If not, then your root is lying between what to where?
C1 and C.
Between C1 and C, isn't it? So you replace your upper limit XU by C1. Initially, you replaced your lower limit by C2. Now your root is between, your XR, the root is between C1 to C2. Can't you imagine that how they are gradually going closer? And they are gradually going closer and eventually they will merge here, okay? How many number of iteration will be needed? That depends on the type of your problem. So this is what your bisection technique, okay? Now in this case, what will be the error actually? You see that initially you are guessing that your root will be lying, for example, between XL and XU. Then if we take the difference XU minus XL, this is equal to say del X0, then we are halving this interval actually. If you are halving this interval, then your error can be there, maximum limit equal to del X divided del X0 divided by 2. And in the next iteration, you are again further halving it. Okay, XL divided by 2 square. In the next case, you are halving it, X0 divided by say 2 to the power cube. In this way, if you keep going on, if you net nth iteration, then the error would be equal to absolute, for example, value of your error would be say equal to simply 2x0 divided by 2 to the del x0 divided by 2 to the power n. Now, if a problem is given where this del x0 can be calculated and an error limit is given there, then you can solve this equation, find the value of n. How many numbers of iteration will be needed to obtain the solution with the specific error criteria fulfilled. Okay, this okay, a blanket decision cannot be made that this algorithm will be efficient and applicable for all the cases. Okay, every algorithm has some deficiencies. Okay, the pitfalls of the algorithm are described in this book. You try to go through it. I hope you'll understand it. The thing is that this error criteria is already there. I have discussed. Then this is what the equation 5.4 that we discussed earlier. By solving this equation, you can find the number of iteration needed. The example that is shown here in this book. Okay, the error criteria was that you have to find the number of iteration so that the root will converge to an error equal to 0.0625, and it has been calculated that the 6 iteration will be needed, and that n should be integer 1. So this is your computer skeleton. You can program it by using your computer to find the solution there. Now another improvement is there. Just in this case, you see that rather than making a what you call a brutal decision there, making half, we can have even a bit efficient algorithm that will help us to find the solution with lesser number of iteration. That is your false position technique, and sometimes it is called regular falsy in your French. The technique is simple. Okay, if you look at this figure 5.12, you see that we have our blue curve. That blue curve is the function which solution needs to be determined. Then you see that this is how the location of the root, and this is your bracket XL and XU. In the case of bisection technique, we just find the next root position by simply halving this quantity XL by XV by 2. But in this case, other than doing this, a straight line is connected between these two. The function values are evaluated at XL and XU, and this line is connected, these 2 points are connected by a straight line. That straight line will be crossing the axis at this point, okay? Can you tell me that what assumption we are doing here? This is not mathematics, actually simple intuitive basis. Actually, you see that between the point XL and XU, you see that your curve is a continuous curve, isn't it?
Yes, sir.
Yes, sir.
Okay, if your XL and XU are sufficiently small, or even not, in this case, if that curve is actually approximated by a straight line, isn't it?
Yes, sir.
Your curve is approximated by the straight line. If your curve is approximated by this straight line and it is intersecting in the x-axis at x equal to say XR, that XR position, XR is actually is not the root, but it can be taken as a false root, isn't it, of your real function?
Yes, sir.
That means the position of the root actually we are obtaining now is actually a false position. This is not the actual position, but that false position will help us to gradually refine this false position so that that false position will coincide with the actual root, okay? So this is what the algorithm called false position technique. The technique is very simple. You see that if we assume that the straight line is the behavior of the function between this upper and lower interval, that we connect them by a straight line, you will see that we have a triangle there, the hash region of the triangles, isn't it? Are not these two triangles similar?
Yes.
If these two triangles are similar, then can we find, for example, the similar triangle ratio, that height divided by base of these two triangles will be same?
Yes, sir.
Okay, then if we do that, then you will find the equation 5.6. Can you see it? Oh,
Yes, sir. Equation 5.6.
yes, very difficult. Today is the 17th Ramadan or 16th? 18th probably.
28th.
Probably 18th, isn't it? Today is the 3rd May.
Yes, sir. Today is the 3rd May.
3rd May. So 14 to 30 is 16, 17. 17 plus 3, 20.
It's 20 Ramadan, sir.
Okay, so
Yes, sir.
we are almost at the end of the 20th Ramadan, and actually very tired. It is very difficult, for example, to continue talking for an hour together or something like this, okay? Okay, no problem. I will be discussing the thing in a way I hope you will understand it. Very simple, no rigorous mathematical formula is needed. So this is what the ratio of your two triangles, okay, base, height divided by base. Then if we rearrange the equation, our objective is what? Our objective, this is actually sometimes you call interpolation type formula. Our objective is what? Our objective is we need to find what? The value of the false position of root, isn't it?
Yes, sir.
XR. Then if we solve equation 5.6 for XR, this is the value of your XR, okay? Here in this case, you see that your XR value can be calculated with the help of function values and the value of your upper and lower gauge that you have obtained, okay? So this is your false position technique. Your false position technique, I will be illustrating these two methods by using a problem from your book. So the rest of the things are there. You please try to have a look. I hope that you'll understand it. Okay. Then we will be going to the open technique in the next class. Let me show you the solution of a problem. Okay, can you see this figure?
Yes, sir.
Okay, this is a problem from your book, problem 5.9. You have to find the value of x of this equation, x square absolute value of cos square root of x equal to 5. Now the thing is that in the bracketing technique, actually setting the upper and lower limit is a challenge, because you have to know that a root is there between these two points, okay, within the bracket. That the one way is you can search randomly, for example, calculate the value of your function in some representative points, and wherever you find that a sign change is occurring, then you can say that your root is lying between these two intervals. This is one way to do that. Another way is that you can plot the function, and that plot will roughly give you where your root is located. So nowadays we have our computer, we have our MATLAB, other programs. So with us, we can plot the function in the wink of an eye. But where I was a student in at your age, for example, say at 1982, at the time no computer was there available. Okay, computer was there, but that computer is not considered. Computer is a very big computer owned by only by few institutions. Personal computers are not available. Okay. I have my hand calculator there. Okay, that calculator can be calculated. We can plot it by using graph paper, and we solve this type of problem at that time. But you see that now you can check it. If you have this function with you, you can plot it, and you have been asked to calculate the smallest positive root. But you may have your root there that can be present in the negative side of your x-axis, even in higher values. If you plot the function, actually, I plotted the function from 0 to 5, where you have your single root. But if you plot go beyond 5, you will find another root there. Maybe some multiple roots could be there. Now, by examining this simple plot, we can find the bracket, that this is the bracket or within which a root is existing. And in order to verify this thing, that our algorithm is working, I calculated the root by using a MATLAB. You just define the function in MATLAB, then you can calculate and find the, you can call a built-in function called F0 to find the zero of your function. This is also a routine for finding the real root. Have you do you have the experience of defining function in MATLAB?
Yes, sir.
Only one or two students is actually responding. I don't know about the others, but the problem is whatever you are doing, the end result will be with you. Be careful about that. Okay, the end result will be with you. If it is good, it will be good. If it is bad, it is very difficult to just rectify. Okay, after your graduation, say you have some problem, you are obtaining a bad grade, probably you will have no opportunity to improve the grade further. Okay, for this reason, actually, you have to engage yourself very fairly and actively in your learning process. Otherwise, nobody can force you to do that. Be careful that even when I was in physical classes, I have seen that in my class, actually, the number of presence is usually high from the very beginning of my early teaching life. But still, I have seen that few students actually appeared in the class just to get the percentage. If percentage constant is eliminated from the university, you will see that only 5 or 10 students will be appearing in the class. But this is how we are also getting this picture by examining your performance in the exam. Only 10% or 20% of the students are engaging very effectively. Others are simply passing their days. I don't know how they are consuming their time at this at this very important part of their life. So this is your function. You can easily define by using your MATLAB. Then you call F0. Initial value should be given there. This is the inline definition of a function. You learn something about the basics of your MATLAB. You need it because now your MATLAB is a de facto criteria for all engineering students. It will not be taught in the classroom. Everyone should have some experience of using it. So your root is this. We need this thing just to calculate the error or estimate how we will be proceeding with towards the root. So if we want to go through, apply our bisection, then what you need to do, we have to calculate the value of the function at x equal to 3 and 4. Then we examine that whether they have a sign change. Then if they are sign change, then we have to half the interval. Then again repeat the process. Then a replacement will be needed in the upper or lower limit depending on the real scenario. Okay, this solution is tabulated here. Okay, I used Microsoft Excel just to solve this problem. You can also do that. I love my computer, okay? Still at this age of 62 years, every day I do something with by using my computer. I don't know how the other students you are doing and other teachers are doing, I don't know. Because whenever I illustrate something, I solve the problem by my own, then I talk about the problem with my student. This is the usual way I do. So this problem I solved, I did not program it in MATLAB because a step-by-step solution I need to illustrate. For this reason, a simple Excel sheet is enough to solve this problem. Okay, your first step is what? Okay, your X. Okay, this is your XL. This is your XU. And when okay, we set a bracket at XU equal to 4, XL equal to 3, then function values are calculated at these 2 points. So your function values are changing sign, isn't it? So your root is between 3 and 4, fine. The next step is what? You have to half this interval. Okay, your C would be equal to say A plus B divided by 2. This is your C. Now next step is what? You have to evaluate the function value at this point. Then your function value is this. Now tell me, if we compare this test of changing the sign, then can you tell me now where is your root?
Between B and C.
Is it not between B and C? Because root will not be between A and C. The reason is that the sign of FA and sign of FC are same. So what replacement is needed? You need not to, for example, use your original A. You can shrink your A to 3.5, okay? You got the point? Then now your bracket is shrinked. Next step is again you evaluate the function values are already evaluated. You can migrate it there. Then you have your function values, again calculate the values there. Now tell me where will be your root? Because your FC value is now positive. Is it not that your root is between now a new C value to A value, new A value?
Yes.
So your positive value is there. You need not to go. That means in the former case, what you have done, this was your XL, this was your XU. We found a value of C that replaced, for example, shrink the lower limit. Now we are finding another value of C that is shrinking the upper limit, isn't it? Now your root is between C1 and C2. You see that this is your real root. Okay, you are gradually going closer to the root. Okay, now you repeat the process and you logically replacement the limit. Okay, and gradually you see that you are arriving at a point where your two value is this. and they are very close to each other. Are not they close to each other? With a discrepancy in terms of percentage is equal to something like this, very small. And you see that at this point, your functional value is nearly equal to 0. So you are obtaining the solution. That solution is equal to 3.7456. Original solution was what? The correct solution was what? What we obtained by using MATLAB, is it not 3.7453? Another problem, okay? This problem I have taken from internet, okay? You see that we have this problem, okay? And within the region 0 to 5, you have your multiple roots are there. So if we evaluate the function, okay, this function is something just to illustrate that if we have our function values both are positive between two brackets. Okay, if we set the bracket 0 to 5, you see that your function value both are positive or negative. As a result, you see that a multiple root could be there. Okay, if we set our bracket from 0 to say 0.5, if we set XL equal to 0, XU equal to 0.5, you will find a root. Another thing is that if you set your XL equal to 3 or XU equal to 4, you will find another root. Okay. In the next slide, we have shown this root. Okay, you can easily examine the solution. We followed the same procedure, and your solution is equal to 3.3963. You can check it. Okay, if you have your problem there, you can check it by just simply redefining the function, MATLAB function that I have given in my first slide. Okay. Now the same problem is solved by using false position technique. So you see that in your false position, lesser number of iterations are needed. But the replacement technique is same. Only the thing is that rather than dividing your finding C by dividing your XL and XU at each stage, here in this case, you have to use the equation that we derived for false position to find the value of your XR. The XR is equal to XC actually. Then according to the sign of FC, you have to make the replacement, okay? Either you have to replace C by B or B by C or A by C. Then you can find the solution gradually with certain value of your what we call precision. And the same problem that I illustrated earlier is again solved by false position technique. Here you can see one interesting thing, that because of the nature of your function, you see that your replacement is only in the one direction. Shrinking is occurring in the one direction, isn't it?
Yes, sir.
Similar problem is, this is one of the what we call special cases. For this reason, actually, sometimes the error that we obtain by differencing XL and XU may be misleading. Here in this case, although the error will be higher, but still we are going to a solution. The reason is that, okay, if we have a function, for example, something like this, here this point is there. In our case, say this was equal to say 4, XU equal to, but here in this case, you see there your function value is such that, okay, it is gradually, for example, moving in one direction only. Okay, it is moving in one direction only because this value of function is replacement is not needed. This type of situation occurs if we have a function something like this. Okay, this is illustrated in your book. If we have fx is equal to say x to the power 10 minus 1, something like this, very nonlinear function in the positive half. You see that if we set a point there, say this is your XU, and set a point there, this is say your XL. Okay, you see that the function value is all the way negative here, okay, but this value is not positive. So you see will be lying. In this case, you see that if we have a function, that function value has a magnitude, that magnitude, say this value is equal to XLU, and that value is equal to FXI. You see that if your XU is very, very greater than XLU, FXL, then where your root will be? In this case, you see that in this case, this is your root, because this region is very small, for example, short in compared with this region. And whenever we are halving our interval, then this point is remaining fixed, and we are moving, for example, this point towards the root, okay? As a result, the difference between XU and XR, the new one, will be higher, but still we are getting the solution, okay? For this region, this error criteria may be misleading is some of the special type of problems. Further discussions are there in your book. You try to go through it to get insight into it. Okay, that's it from my part. It is very difficult for me to continue now. Please stop recording.